Welcome. This is a recording of a webinar that we did last week in Chapel Hill, but what happened was the audio had a little bit of an issue, and so I'm actually just recording some of the topics that we talked about in response to a request for linear data analysis for our Math 1 students here in North Carolina. My name is Maria Hernandez, and I teach at the North Carolina School of Science and Mathematics. And so hopefully these materials will be useful to share with your students, and also maybe even to provide some discussion within your professional learning communities. So what I'm going to do is we're going to work through a task, and if you have your calculators handy, it might be useful for you to take those out so that we can type the data into the calculator. I'll go through that using a calculator emulator, so if you have a TI-83 or an 84 or maybe an Inspire, you can work along with us. The other thing is that the webinar, at some points, we had input from our audience, and since I don't have that now, I'll just probably stop and talk a little bit about some of their responses. And of course, as you work through this, you might think of different things in terms of what your focus might be when you work through the task, or talk to your colleagues about the mathematical task, and in particular the mathematical practices for the Common Core State Standards. So the goals for this session are to work through the mathematics for a real-world problem, and to build the ideas of how to determine what a best fit, what do we mean by a best fit. So the students, in our case, might be hopefully presenting their own ideas as to what might determine goodness of fit, and we're going to work through a problem, like I said, and then also to think about how we are actually implementing many of the mathematical practices from the Common Core State Standards as we work through this real-world task, not so much just to teach students a particular procedure, but to help them understand a big concept, and then to be able to present their ideas, support their ideas, and also listen to the ideas of others and critique the ideas of others, and also to share some web resources related to the topic. In addition to this taped webinar, the PowerPoint will be available, and the handout that has the task on it. It also has calculator steps, so if you're new to using the 83 or 84 for data analysis, hopefully those will be useful to you later. As we work through the task, what we want to do is think about how our students will approach the problem to anticipate their responses and questions, and consider how we can use their ideas as in their contributions to build the mathematical topics. So it's not so much about just putting forth these particular procedures or these criteria, for example, for goodness of fit, but instead thinking about, as the mathematicians produced these processes, how did they think about these different viable answers to the problem, or the solutions to the problem. So here's our first example. The data comes from the Journal of Environmental Health, and it shows the health hazards that may have been caused by an atomic energy plant in Hanford, Washington. So the plant was producing plutonium, and much of its waste had to be stored underground. The waste has since seeped into the Columbia River and exposed the area surrounding Hanford to radiation. The data below, it's actually on the next slide, shows the number of cancer deaths per 100,000 residents in the 9 exposed counties that were contaminated. So if you look at this data set, it looks like they've recorded some kind of index, and the names of the counties are across the top, and then the deaths per 100,000 related to cancer. So these indices it's not specific as to how they're calculated. If you're interested in that, I do have a resource at the end of the PowerPoint that has a link to a website that tells you the details of how that index was calculated, but supposedly it's related to how close the residents were to the area of contamination. So the first question says which variable should be the independent variable and which should be the dependent variable, and to explain your answer. And then it also asks you to use your own knowledge of linear functions to create a linear model that you believe is a good representation for the data. It says do not use any regression buttons on your calculator or other technology, and to show your steps. So the first question, when I asked this question last week, one of the teachers responded by saying, well, the independent variable should be the index, because that is related to the proximity of the residents to the contamination, and then the number of deaths per 100,000 would be the dependent variable. So if we're thinking about plotting this data, we think about the index along the horizontal axis and the number of deaths per 100,000 residents on the vertical axis. So this is a calculator graph that was produced using the TI calculator, but I'm going to escape out of here and go ahead and type this data into my emulator here so that you can see how to do that, and also produce a scatter plot of the data. So I'm going to hit the stat button. It's here in red, and I'll hit enter. Let me put large screen here because you don't need to see the calculator steps, I don't think. And then what I'm going to do is I'm going to type in the index, and if you wanted to look at this webinar while you have the handout, that might be a good idea. That way you'll have the data in front of you as you work through the problem. So 2.5, 2.6, 3.4, these are in various counties, 1.3, and I'm just putting that into that first list, which is entitled List 1, or L1. And then in the list adjacent to it in L2, I'll type the corresponding deaths per 100,000 due to cancer. So 147 and 130 and 130 and 114 and 138, 162, 208, and 178, and finally 210. So if I want to produce a scatter plot like the one you saw in the PowerPoint, I'll go to second y equals, so I'll click on the second button and then y equals, and I'll turn the stat plot on. To do that, I'll hit enter, and I'll hit enter while the cursor is flashing on, and then in the next one I can choose what kind of plot I want. For example, there's a scatter plot, that's the first one, that's the default value. There's histograms, there's the box and whisker plot, etc. So I'm just going to arrow down since it's on scatter plot. And then in the independent variable I want list 1, so I would type second 1. It's already on L1, but I'm just showing you in case that it wasn't on L1. And then it'll move down to Y list. I'm going to do second L2, and then you can choose your mark for your scatter plot. To choose a window, you can do one of two things. You can actually look at the list of data and decide on a window based on those values, or you can also use the feature on the calculator which is called Zoom Stat. If you hit the zoom button, which is right here in the middle of the calculator on the top, and then arrow down to the 9th choice. Oops, I've gone too far. Then the calculator will choose a window based on the scatter plot that you have turned on. So it's kind of smart enough to look down the list and say, oh, this is an appropriate window. If you want to use your calculator to do that window for you, you can just hit zoom 9 or zoom and then arrow down to the 9 and hit enter. And there it is, and that's the graph that you saw on the PowerPoint. I'm going to change the window because I like to see my axes. So if you'll notice, I hit window and this x-min is set to 0.7. I'm going to choose 0 so I can see the y-axis. And similarly, I'm going to change my y-min to 0 so I can see the x-axis. I'm also going to change my scale because the y-max is 226, so I don't want quite as many tick marks in there. It's kind of squashing them in. So let's change that to 20, for example. And then if I hit graph, it produces a nice graph, and now I'm oriented in the world. I can hit trace, and I can see my data points. There's the 2.5, 147, etc. I'm just hitting the right arrow key to trace through the data. So in the problem, in the task, we asked the students to come up with a function that they believe, a linear function that they believe would be appropriate model for the data. And so this is a really nice opportunity to think about, without hitting any what I call magic buttons on the calculator, the linear regression button, for example. You want to just think about what would be a good representation for this data set. So one of the comments that was made last week by one of the teachers was that they had just studied y equals mx plus b, that is slope-intercept form. So students might start actually with the intercept and think about approximating an intercept and then tweaking the slope, or maybe using 2 points to kind of come up with a slope, and then kind of fine-tune it from there. So that was an interesting comment. Another thing that was noted was that maybe some students would say, well, I want a line that goes through this data that somehow splits the data in half. That is, the same number of data points would lie above the line as below the line. And also reasonable answer. Another suggestion was that maybe I would try to choose a line that would go through as many data points as possible. And that, of course, depends on whether or not any of these points are, in fact, collinear, or many of them are collinear. And if you did that, what would that mean? Would I choose, for example, that's one that's flashing on here, 1.3114, and then maybe this one, this 3.8162, and then come back down. I guess I have to go backwards. If I thought, well, these three down here look collinear, that one, the previous one I just showed you, and then that one, then would that really be a very good model? Some students might say, no, it's not such a great model because it will have a steeper slope than kind of the rest of the representations of the data would present to us. So one of the things I did was I chose 2 points and I came up with the equation of the line. But our job in the rest of the task is to defend our line. So let's go back to the PowerPoint. I chose the point 2.6130 and the other point 6.4178. So it's nice algebraically to think about getting the kids to find the slope of that line using the definition of slope, the change in y over the change in x. And then using the point slope form of the line, once I have that slope value, I'm going to plug in either one of these points, 2.6 and 130, or in this case I plugged in 6.4 and 178 and did the algebra here to find this intercept. So what we might do now is actually type this into the calculator, 12.63x plus 97.17. So, sorry, I'm going to go back to the emulator, and I'm going to go to y equals and type this line in there. 12.63x. But you, of course, might have a different line, and this is where you might want to stop and have folks come up with their line, maybe not based on these particular 2 points, but 2 other points that they think are representative, or use the idea of slope, and then think about a slope that might be appropriate, or using the idea of y-intercept and then tweaking the line from there. So this is my particular model, but each student might have a different model. And if I hit graph and then start thinking about the criteria for the different possible criteria for determining line of best fit, like I said before, some of the folks said, well, are the same number of points above as below? In my particular case, the answer is no. It looks like it goes through 2 points, and it looks like from the graph at least that I have 1, 2, 3, 4, 5 above and 2 below. So some students might say that's not a great criterion. This last point out here to the right seems a little bit problematic. So if you pulled your line towards that point, mine wouldn't get better according to that criterion. Another thing that was brought up was the idea of thinking about error. So that's a great idea. Think about, how are we going to measure error? How far, for example, are these data points from the line? So that one that is flashing on right now, that 2.5147, how are we going to measure that distance? We think about perpendicular distance. And a comment was made that in geometry we talk about the distance from a point to a line, and we are talking about the perpendicular distance. But we could also talk about the vertical distance. And a great comment was raised when we had our webinar last week, because someone said, well, when you think about it, that line has a representative for each of these points, And that line's representative could be you could get your hands on that representative by saying, well, let's take all the x values for each of these points and substitute them into our function, in which case you'll get definitely a point on the line, and it'll be the representative that's associated with each of those data points. So that was one of the suggestions we had, and we can do that easily in the calculator, so let's do that. Let's hit Stat and hit Enter. And now what we're going to do is we're going to arrow over here to L3, but go to the very tip top of L3, and what I'd like to do is think about evaluating my model, that is that linear function, at all of the x values. So if you'll notice in the middle of your screen that y1 is my model, that's where I stored it, 12.63x plus 97.17. I could certainly type in here 12.63 times L1 plus 97.17. That would take each of these x values and substitute them into the function, but not so much substituting it in, but actually calculating those values all at once. Once I hit enter, it can do that. If you want to think about it more from a function standpoint, what I want to do then is evaluate y1 at each of these x values. So what I'd like to do now is show you where you can get your hands on that y1 variable. So I'll go over to vars and arrow over to yvars and choose function, and then you have access to all of the functions that are defined. So in this case it's y1. Notice I'm at the top of L3, so you can see the command is at the bottom of the screen right now, y1. It's waiting for me to do something, and I'd like to evaluate y1 at all of these x values. So I'm going to type y1 of L1. This actually emphasizes function notation. My students sometimes will say y1 times L1, and I'll say, no, that doesn't really make sense. We're not multiplying the function by anything. We're actually evaluating it at x values. And in one fell swoop, with this command at the top of L3, my calculator can do that if I hit enter now. So all of these y values right here are what one of my participants suggested were these representatives on the line. And so if we go back to the graph or look at the middle of our screen here, you can see that we can think about the vertical distance. Now, the vertical distance from some point to the line is easy to come up with now, because the y value of that point, for example, that it's on right now is 147, and all I have to do is subtract from that the y value that corresponds to that x value on the line. So what we're actually defining here is what's known as a residual, and a residual is defined to be the y value of the data minus the model evaluated at the x value of the data. Another way to put it is actual minus predicted. The prediction is, sorry about that, the prediction is the y values that I currently have inside of my stat list in L3. So if I want to think about where do my y values, actual y values, live in L2, and then these predicted values live in L3, so I'm going to go to the very top of L4 and calculate residuals by saying the residuals for this entire data set and this particular model will be actual y values, which are L2, so I'll type in second L2 after I'm at the tip top of L4, and then subtract from that the values that I calculated in L3, which are the predicted values. So these are known as residuals, and again, each model will have a different set of residuals. So if you have a different model, your residuals aren't going to look like mine. They're going to be different numbers. But the whole point of this is to try to defend why you think your model is very good, and this is one way that we might have access to some quantitative data that says my model is better than yours because, and then you could fill in the blank. One of the things that could be in the blank is, well, my residuals are smaller. But you might say, well, I don't know why this keeps coming up, sorry. You might say, well, I've got a whole list of residuals. How can I compare my residuals to somebody else's residuals? So some folks last week said, why don't we add all the residuals together? And then if your sum is closer to 0 than my sum, then I'll concede that your model is better. So that was an interesting idea. And if I go back to the graph and again think about residuals being summing to 0, it would mean that my errors, so again let me hit trace, some errors could be very positive and some errors could be very negative, in which case I'd add them all together, and if it was close to 0, you still might have some issues kind of deciding whether or not your model was very good. Because again, you could have some big errors and some small errors, and the fact that you have negatives and positives in there could kind of cancel each other out. So another suggestion was that we take the absolute value of those residuals and then add them together, because then you really are looking at true error and you aren't taking into account the fact whether there's some are positive and some are negative. You're making everybody positive so that when you add them together, you're not losing, in a sense, some of the error. Another thing that was suggested was that we square those errors, because another way of making things positive is to square them and then add them all up together. So those were all great ideas. I am going to go back to the stat editor and say, well, it's easy enough to take this list of values here, take the absolute value, and then add them all together. So let's go to the tip top of L4, and let's just calculate the absolute value of all these, again, all in one fell swoop, by hitting the absolute value key, which you can find under catalog. Let's do second catalog, and it's actually the first choice there, ABS. And we're going to calculate the absolute value of L4. And notice it will replace the current L4 with the absolute values of these errors. And now what I'd like to do is sum all of the values in L4 now that I've gotten rid of the sign. So if I go to my home screen now, I can either go under catalog and use catalog to find sum, and you can sum the entire list. So we'll do second catalog. I believe I hit S here, it will go down to the S's, and I just need to arrow down to the sum command. A lot of S's. Almost there. Another way you can do it is do one variable statistics on the entire list, but you get a lot of information there, and I didn't want all that information. So now if I hit sum here, I can do second 4, which is L4, close my parentheses, and then now we have one single number to represent our model and how good it might be. So one of the things you might decide on is to have everybody do this for their model. Take the absolute value of the residuals and add them all together, and then the person with the smallest sum could get a prize. For example, we could say, yes, that's the way we're measuring our best fit. The other suggestion was to square these and to sum them all up. That's another way to make things positive, is to square them, and that actually is the criterion for which the least squares line is based, on which the least squares line is based. So if you think about it, it makes sense. The words are least squares, because it minimizes the sum of the absolute value of the residual. I'm sorry, it minimizes the sum of the squares of the residuals, and that's what's going on in your calculator when you hit that linear regression button. There are, of course, formulas it's using to calculate the slope and the intercept of that, what we call the best fit line, but it's using the criterion of minimizing the sum of the squares of the residuals. Another question that was raised that I didn't have an answer to last week, but I do have an answer to this week, was, will you get the same line if you use that criterion of minimizing the sum of the absolute value of the residuals? And the answer is no. You do get different lines. Minimizing the sum of the absolute value of the residuals gives you more kind of a median result, as opposed to this one that's more based on a mean. So I'm not going to go into the details of that, but I did ask a colleague here, a statistician, and they gave me that information, that you actually wouldn't get the same line. But when you push linear regression button, it's giving you the line of, we call best fit, but it's based on that criterion. So what's great about this, I think, this activity, is that students have had an opportunity to come up with different criteria and to support and to defend their own ideas and to listen to the ideas of others. And then ultimately, they're hopefully going to understand what's going on in terms of the geometric interpretation of residuals, and also this idea of, you can move lines around and you can see where some of the residuals will be much larger than others, and what that linear regression line is trying to do is minimize the sum of the squares of the residuals. So I have provided a couple of different resources in terms of applets that will let you play with a data set and move those lines around, and I'll show you probably one of those near the end of the presentation. So if we go back to the PowerPoint, here's a scatter plot with my particular line, and then this is the opportunity for you, maybe if you're watching this in your PLC, to stop and talk about what your students will do here. If you ask them to compare their models to their neighbors and to say who's better, think about what kinds of explanations they'll have, what kinds of questions they'll have. Maybe they'll have some trouble in terms of using mathematical vocabulary, and this would be an opportunity for you to kind of step in and provide some guidance there. And then, to stop here if you're in your PLC, to stop and list some other measures of goodness of fit that you think your students might kind of come up with that I haven't mentioned here. Another thing that I wanted to mention in terms of the residuals is the way I define residuals are actual minus predicted. And when I got rid of the signs because I wanted to add them together, I got rid of some information that is actually kind of useful. So we might not want to do that all in the same list. You might say to your students, what does it mean to have a negative residual? So in terms of the data set, that if they have that geometric picture of their measuring how far a data point is from the line, that vertical distance, if you leave the sign in there, then it's not so much distance anymore, because we know that distance can't be negative. But if you have a negative residual, it means that your point lies below the line. If you have a positive residual, it means that the point lies above the line, so that information could be useful as you're thinking about making predictions or calculating a single residual from your model. So again, we talked about lots of these things already. How do we measure error, and how can we find a single measure of error? When we calculate residuals for any model, you're going to have as many residuals as you have data points. So calculating residuals can be useful, and we'll talk about creating a residual plot. But if we just want one measure, we needed something else, and that's where the idea of summing the absolute value of the residuals or summing the squares of the residuals came in. To find the residuals, we've already done that. We calculate the residual, actually the residuals associated for the entire data set. I can show you how to do just one on the home screen, and then also we can compare our residuals for the entire data set. So let's go back to the emulator, and let me just show you how to calculate a residual on the home screen for a given point. So say, for example, I wanted to know what's the residual associated with the first data point, 147, 2.5. Just on the home screen, before you even calculate the whole list, you could show students that what I'm doing is taking the y value of the data point, 147, and I'm subtracting that from the model, which was vars, y vars, function, and then choose wherever you've stored your function, evaluated at the x value, which is 2.5. So this is useful to do sometimes before you actually create the entire list, so that students get kind of more of a feel for what it means to calculate a residual. Y value of the data set minus model evaluated at the corresponding x value. And so then again, I could say, why is it positive? And then, is this a big residual? Well, it depends on y values of the data set. So we'll talk in the next webinar, which will be on nonlinear data analysis, but you can do it for linear data analysis as well. Talk about percent error. If you want to think about how big is 18 very big? Well, you could divide it by the y value of the data set, and that gives you some kind of a scaled value, and multiply it by 100, and that will give you a percent value. So that's the percent error. You have 12.4% approximately with that particular data point. Let's go ahead and do a stat plot of the residuals so you can see how to calculate a residual plot. So if I go over here to my stat plot, what I'd like to do is think about where my residuals live. Oh, I've lost my residuals, so I'm going to go back, because I got rid of their sign. I'm going to go back to L4 and just recalculate those real quick. So I've gone to stat and then hit enter, and I'm going to type in actual y's minus predicted. And then now I can plot these values, and now the signs are associated with these residuals. So I'm going to go to second y equals and turn a stat plot on that will show me the residuals. So I'm just going to go to this very first plot, hit enter, and arrow down here. I want my x list still to be L1, but I want my y list to be my residuals, and my residuals live in L4. So I hit second 4 and hit enter. I'm going to go to y equals and turn off my model, because these are going to be a plot of the errors. So this model doesn't make sense to have it on the same screen. And now I can hit zoom, and again, if you go arrow down to 9, you can choose zoom stat, or you can just hit the 9 button here. And there you go. This is a plot of my errors with a sign associated with it. So you can see the residual plot, and then next webinar, in January, we'll talk a lot about if you try to use a linear model for a nonlinear data set, what will happen in terms of this residual plot. So let's go back to the PowerPoint and just think a little bit about how this idea of using functions to represent your data can be a very useful tool now as students learn more about linear functions. What I've done here is I've replaced my y's and my x's with letters that have some meaning and context. So I let D be the deaths per 100,000 due to cancer, and I be the index based on the proximity of the residents to the contaminated area. And now you can use your model to make a prediction. You can do things like interpret the slope and the intercept of this model in context. So for example, if I think about that 12.63, that's the change in the dependent variable over the change in the independent variable. So we might say as the index increases by 1, the number of deaths per 100,000 increases by 12.63 approximately. And the y-intercept is if the index is 0, how many deaths due to cancer will we have per 100,000 people? That would be 97. So what I would do in terms of using this as an opportunity for students to write their ideas down, it gives them an opportunity to think about how slope and intercept have these geometrical interpretations, but they also have contextual interpretations if your data is real world data and your model is representing that data. So in terms of mathematical practices, I'm hoping that this task gave you an opportunity to think about engaging our students with these mathematical practices. And again, if you are in your PLCs now, you might stop the video here and have a discussion about which of these we've kind of presented or given students an opportunity to engage in. So definitely making sense of problems and persevering in solving them. The model, we modeled with mathematics. We used a linear model to represent the data. Various of these have come into play, and when it comes to attending to precision, it's actually interesting because many of us think about precision as numerical precision because we're mathematicians, but I think also it's really important to go back and read that standard. A lot of that has to do with precision in vocabulary and presenting our ideas and presenting our methods. So again, I think this task is rich in the sense that it can give our students lots of opportunities to engage in these mathematical practices. In terms of the Common Core State Standards that we have addressed here, particularly in statistics and probability, we have kind of had an opportunity to represent the data on two quantitative variables in the scatter plot, to fit a function to it, but it's not just a function by hitting a magic button, but instead using our algebraic skills and our knowledge of linear functions to come up with that model. Also, we've talked about residuals and plotting those residuals and analyzing them, and we'll do more of that in the next webinar. and fit a linear function to a scatter plot, etc., interpreting slope and intercept. And then in terms of functions, we've also had an opportunity to address some other content standards in terms of the functions, particularly because we have a contextual problem. We can interpret the parameters and also think about function notation and evaluating functions for inputs in the domain. You might ask your students, over which domain is this function appropriate to use? Again, a linear function normally has all real numbers as its domain, but for this particular context, what domain does it make sense to think about the function on? And then for that domain, what's the range? So hopefully those will be interesting questions for your students to answer. Also, we didn't make a prediction, but you could make a prediction using your model. For example, we could either take one of the index values in the data set or extrapolate and choose a particular index outside of the data set and say, what would your model say in terms of predicting the number of deaths per 100,000 based on this index, which again is based on the proximity to the contamination. In terms of exploring some math tools, NCTM has some new tools called Core Math Tools out, and they're very nice in terms of providing you with lots of different data sets and then also tools for examining those data sets. So here's an example. They have some hamburger data. They even tell you where you can buy these hamburgers, and they give you the calories. Don't look, some of them are as high as 970 calories, and also the fat and the carbs in the calories. So I can't remember which one of these is along the horizontal, but you can choose, say for example, the fat, and then plot the calories along the vertical axis. I think that's what's calories on the vertical. Yeah, fat is on the independent axis. And then you could ask your students to come up with a linear function for this. Let me escape out of here, and I will see if I can just start up that tool. You can download the tools onto your own computer as well, but they're called Core Math Tools. Looks like they were funded through NSF. And when it comes up, you can access them from the NCTM site, and I have that link at the end, or you can, like I said, download it and run it off your own computer. What I've got here is, if I go to the hamburger data, this first one, and say OK, then it produces a graph, and I can choose fat along the horizontal axis and calories along the vertical axis, and it produces a nice graph for me. Also, these are really nice. I can do a hand draw a movable line, so I click on that pencil, and I believe, yeah, I can move it using this tool where I'm moving the y-intercept with that box, and I'm moving the slope here. So this is kind of a nice kind of way to eyeball a line. You can also ask for the linear regression line, which is this one, or you can ask for a residual plot. It's not so much a residual plot, but it's just showing you these vertical distances. Or you can ask to show them in terms of the squares, because think about it, you're minimizing the sum of the squares and the residuals. Now you can move your line around and see how those change. It's a pretty nice tool. And then also you could look at a residual plot, which is this one here. It says if you hover over them, they'll tell you what they are, and it opens up a new window. And I think it's supposed to draw a residual plot. Not sure why it's not working. Maybe it only does a residual plot for the linear regression. Let me close it and put the linear regression on there. And then you can see a residual plot. Yeah, there you go. Actually, it's got both of the lines. So the red one here is the 12.928, and then the blue one is the 16.363. So one of them is the residuals for your linear regression. The other one is for the one you created just by eyeballing the line. So, and then if you just click it again, it's a toggle, so it just turns that off and just leaves you with the original line that you were just eyeballing. If you go over here to the right under question mark and you click, it gives you all kinds. Oh, I thought this just gives you help on how to use it. So this is really, it's a very nice tool. You can copy and paste this into a Word document. Say you were making up a quiz and you wanted to ask a particular question about a residual plot, or just have a nice data set that you can graph and use it in a quiz or a test. It's really nice. Also, there are all kinds of nice data sets in there and explanations of those. So that is under the core math tools for the NCTM tools. These are the various representations that I just showed you. And then here's an activity that we created here at the North Carolina School of Science and Math, but it's based on an activity that Gail Burrell wrote about in 1996 in the mathematics teacher, and I have a reference to that. These are different. These are more modern people than she had in her her activity. But what you do is we have a PowerPoint where we show these famous people and we ask students to guess their age, and then we tell them how old they really are, and then we ask them, how good a guesser were you? So it gives them a really nice opportunity to think about measuring error, because they all have their own data set, and if you ask them who the perfect guesser is, or if there is a perfect guesser, then what that would mean. So they get to think about that the line y equals x would mean that if you graph guess along the horizontal axis and actual age along the vertical, or vice versa, that the line y equals x would mean perfection, because it would mean that you guessed everybody's age precisely. So of course that doesn't happen usually, and so it gives them an opportunity to, again, to think about error, and opens the idea of the door to residuals, and is a fun activity that kids seem to like. So in this particular activity, we give them a chance to write a sentence to describe what kind of a guesser are you. Maybe you overestimated everybody, maybe you underestimated. Maybe you underestimated for people that were young, and you way overestimated for people that were older. That's what teenagers tend to do. When I show them older celebrities, then they tend to do that. So again, it gives them a nice opportunity to chat about their mathematical ideas. And again, this came from the mathematics teacher from September 1996, from a great article that Gail wrote. Another nice little tool is a Geometers Sketchpad demo. It's just on the web, and I have a web address for you. Again, it shows you there the total sum of the area of the squares, and it shows you the sum of the squares, the residuals, and each of those squares. And you can play with the data points and move a data point around, and then see how it affects the linear regression line, or it affects that total area of the squares. And so here are the resources that I mentioned before, and they will be available on the website. The linear data analysis tasks that we've created are up on a website that has various data sets, and actually classroom ready handout and a teacher handout with solutions in there. The NCTM core math tools that I showed you, and those are the couple of least square demo sites that I found useful as I teach this topic for students. So stay tuned, please, for the next webinar if you'd like to join us for nonlinear data analysis. It's going to be January the 18th, 10:30 to 11:30 in the morning. I know that's probably a time that some of you are teaching, but don't worry, it'll be archived, and hopefully the sound will work just great. I think I'll be in Johnston County for that, and it will be kind of picking up with the ideas that we've started out talking about here with residuals, and in particular talking about nonlinear data. Because if you look at the Common Core State Standards for Math 1, or the State Standard Courses Study for North Carolina, students do have to be able to recognize the difference between different kinds of data sets in terms of when's a linear model appropriate, when's a quadratic model appropriate, when's an exponential model appropriate. So hopefully I will have some tasks for you, and I'll try to have that handout ready. If you want to email me or Carol, I have my email address on one of the slides, and Carol will too. Carol Stern is in our distance education department, and she is the one you register with, in which case she will send you the handout before the webinar, so if you'll have a chance to look at that ahead of time. And then of course if you want to bring your calculator and join us at that same time, that would be great, or maybe watch the archived version in your PLCs or at another time at your own convenience. So thank you very much for watching this. I hope it's been useful. Again, there are emails, and we're happy to answer any questions that you might have in terms of these resources. And as usual, I'd like to thank the folks here at NCSSM for putting the funds together, actually, for me to be able to do this as part of a release time, and be able to do it throughout the school year, hopefully presenting you with tasks and ideas and food for thought as we try to implement the Common Core state standards throughout the year. Thank you.